Hi everyone. In this video I'm going to apply some transformations to different basic exponential functions. So really the new part here is what does the basic function look like? The transformations are exactly the same as before, but exponential functions work a little differently. Your inputs always go in the exponent, so there is a little bit of practice involved with spotting what's affecting x and what's affecting y. So let's just go ahead and look at this first one. This first one, I see the basic exponential function. I know it's exponential because the variable is in the exponent. I see the basic exponential 1/4 to the t. So I'm going to start with 1/4 to the t. So we should know, this is our first job for this graphing section, off the top of our head what that looks like. So we should know that they always, the basic exponential functions always have horizontal asymptote at y equals 0. Because our base is between 0 and 1, we're going to get this general exponential decay shape. So I can kind of rough sketch that in. And then we can get as many points as we need. This is always an easy one. The y-intercept of the basic exponential function is always 0, 1. That will change when we apply certain transformations, but for this one, it definitely still is 0, 1. And I'm going to go ahead and snag -1, 4. You can use whatever points you want. I generally just use 2 because I'm also following the horizontal asymptote, and I feel like that gives me 3 things that make sure my graph's in about the right spot. The transformations I see, so again, the way an exponential function works is whatever you input goes in the exponent. So this 3 up here with the t is affecting t. That's a horizontal shift. And since it's a +3, it will be to the left 3. The 2 is not in the exponent, it's out in front. It's multiplying the entire 1/4 to the t function. So that is a vertical stretch. So we're going to double our y values and we're going to subtract 3 from our x values. So as always, you can do these each separately, or if you're comfortable, feel free to combine them. Let's see here. Vertical stretch should happen first. So always shift last. This is one where it wouldn't get you in trouble if you mixed up order, but to be safe, it's always good to shift last. So I'll go ahead and do one scratch work graph to get the vertical stretch. Stretching away from the x-axis is not going to move the horizontal asymptote because it is on the x-axis, even if mine looks slightly below. If I stretch the y-intercept 0, 1 by a factor of 2, it's going to end up at 0, 2. And then the point -1, 4 is going to end up at -1, 8. Okay, so we'll say that's around -1, 8, right around there, so fairly steep. So we doubled all of our y values, so it's going to look steeper in quadrant 2, and it's going to be farther up from the y-axis in quadrant 1, I'm sorry, from the x-axis. And then we need to shift everything to the left 3, so this was -1, 8. The shift to the left also won't affect our horizontal asymptote, so we still have the horizontal asymptote along the x-axis. Make sure you draw and label your horizontal asymptote every time. I will be checking for that. That's one of the ways you can show me that you really followed and didn't exclusively get information from your calculator. 0, 2, if I shift that to the left 3, it will end up at -1, 2, 3, 2. And -1, 8, -1, 8, if I shift that left 3, it will end up 1, 2, 3 right here at -4, 8. So my basic shape, looking pretty steep over here, and then working its way down towards that horizontal asymptote. Okay, so there's a sketch of m of t. So every exponential function should have that horizontal asymptote and should either have the exponential growth shape or the exponential decay shape when you're done. Okay, so for part B, the basic function that I see, let's see if one of my other colors is working for me today. No. is 5 to the x, 5 to the t. So now I'm starting with an exponential growth shape. So again, if you can keep the details in your head, you don't have to reproduce this for me, but I want to make sure that you see what I'm picturing in my head. So I'm going to follow 0.01, the horizontal asymptote, and 0.15. You can use any points. I'm just trying to snag a couple that seem easy to follow through transformations. So this is the new part. This is the number one thing to be working on. The number two thing is spotting what's affecting x, what's affecting y when you're looking at the transformed equation. So here I have a negative sign attached to my t up in the exponent. So that's affecting my t values, which are my x's in this case, which means it's a horizontal flip. So we're going to flip over the y-axis. The -2 is not in the exponent, so that's getting subtracted from the entire 5 to the t function, which means from my y values. So that's a shift down 2. Okay, so again, up to you. If you're comfortable combining steps, please do. That's great. If you're not, keep them separate. So I'm just going to do a really quick sketch of the flip. When I flip upside down, oh, hold on, let me be careful. We're not flipping upside down. We're flipping over the y-axis. So when I flip across, it's going to switch from looking like exponential growth to looking like exponential decay. And actually, algebraically, if you want, you could say 5 to the negative t is the same as 1/5 to the t. And you could start right off with that decay shape. I don't have a preference. Either of those is fine with me. So either start with 5 to the t and flip it, or you can recognize the algebra there that would turn that into a 1/5 to the t. Okay, so it's flipped across. So there's kind of big picture. 0, 1's going to stay put. Flipping the horizontal asymptote doesn't change it. And 1, 5 ends up at -1/5. I then need to shift down 2. So this one will no longer have a horizontal asymptote at 0. The horizontal asymptote will be at -2. You really want to make sure that you follow that. Some people will follow their points correctly and get really confused because they're still trying to have an asymptote along the x-axis. So for example, 0, 1 shifts down to 0, -1, and they're kind of baffled with how to make that work with an asymptote at y = 0. -1/5, when we shift down 2, will be at -1/3. So my shape ends up looking something like this. Okay, so shifted exponential decay shape. Okay, last one here. P of t is equal to -e to the t over 2. So you may or may not have run into this e business before. I don't want to make a huge deal about it here, but I do want you to be aware of the fact that e represents a number. So this is similar to pi. Pi represents a number that's approximately 3.14, but we give it a symbol because it has a very precise meaning and we don't want to lose information by rounding every time we write it down. And because it's a non-repeating, non-terminating decimal, we can't write that all out. E is the same idea. If you're curious, I'll tell you where it comes from. This becomes really fascinating in calculus. We'll come across E in calculus, and it's a really nice number. So if you take 1 + 1 over x and raise it to the x, this will approach E as x approaches infinity. So the idea here is if you start plugging in bigger and bigger numbers for x in both spots, you're going to start getting the decimal places of E. And I can even show you this. E is on your calculator. In fact, on the TIs, it's in your calculator in 2 places. What is happening here? Let me clear out all my nonsense. Okay, so if you hit second and then the division symbol, there's an E. And then if you hit enter, there's the decimal approximation. 2.718, and it actually looks like there's kind of a pattern starting, but there's not. If you look at more decimal places, you'll see that we lose this nice 1828 business that seems to be starting. So The other place that you can find E on your calculator is the second button and then this natural log ln key. We'll do logs in a little bit, so we'll use that one too. The only difference is this one automatically sets you up to put an exponent on your E, because we do E as an exponential base. That's really interesting. So we use powers on E a lot. So if you know you want E squared, you could save yourself one keystroke by doing that instead of just typing in E with the caret. So second E to the second would also work, either one of those. Okay, so again, the way we get these numbers to show up, 2.71828, so on, is by picking really big x values and plugging them in here. The bigger the x value gets, the more decimal places of E you'll get. And the reason this is such an interesting expression is because as x gets really, really big, this part right here is getting really, really close to 0. It's not 0, but it's very close to 0, which means the stuff in the parentheses is getting really close to 1. If the stuff in the parentheses was just plain old 1, then raising it to powers isn't going to make any difference. It doesn't matter how big the power is. 1 to any power is still 1. But our power is a huge, huge number, so this is going to infinity, and our base is not exactly 1, it's very slightly bigger than 1. So there's this weird tug of war that happens where huge powers make your numbers blow up and get massive, but base of 1 makes your number not grow at all when you raise it to powers. And it turns out that neither one wins. They kind of tie in the middle, maybe win one a little bit more since we're not that far off from 1. But we get this nice decimal, non-terminating, non-repeating decimal, irrational number. Okay, so really all I need you to know when you see an E for now is that it is a number. It's approximately 2.7. Otherwise, I just want you to get used to seeing it. We'll talk about it again when we get to natural logs. So this is just a familiarity thing and a basic idea of what the graph looks like. So here, I start with the basic function y equals e to the t. And that's perfectly valid. There's nothing in our definition of exponential functions that says the base has to be an integer. Pi could be your base as well. The square root of 7 could be your base. Those are all legitimate. E to the t. So again, you want to be thinking E is approximately 2.7, so a little less than 3, which means E to the t is going to look quite a bit like 3 to the t. So if you kind of imagine what a 3 to the t would look like, it would go through 0, 1, it would go through 1, 3. You'll be close to on the right track. E to the t will in fact go through 0, 1. E to the 0 is still 1. It will not go through 1, 3, it will go through 1e. And that's how I want you to label the point. I don't want you to label it approximately. I don't want the 2.7 there. Just say this is exactly at 1e. So you have to approximate when you're placing the point and say, okay, around 2.7. But to say exactly where it's supposed to be, you use the e in your label. Transformations I see, the negative sign is not in the exponent, so that's affecting y. That's a flip over the x-axis. So there's the flip upside down I was trying to do last time. And then the division by 2 is in the exponent. So this is the same as having a 1/2 t. T divided by 2 is the same as 1/2 t, which means that's horizontal stretch by 2. Okay, so I'm going to go ahead and do the flip upside down. So basic shape is just upside down version of what I had before. The asymptote doesn't move. We're flipping over the asymptote. The point 0, 1 ends up at 0, -1. And the point 1e ends up at 1, -e. And again, I don't want a decimal approximation. I want you to keep that exact. Tell me exactly where it's supposed to be. If I want the approximate, I will go looking for it. I'm then supposed to do horizontal stretch, so this is going to change x values. If I stretch the horizontal asymptote, it doesn't make any difference. Making a line that's infinitely long, twice as long, doesn't look very impressive on our graph. 0, -1 also doesn't move. That's on the y-axis. We're stretching away from the y-axis, so it's actually fixed. But 1 -e will move. I am doubling my x, horizontal stretch by 2, doubling my x, so it's going to end up at 2 -e. And again, we have to approximate when we're placing the point, so a negative 2.7-ish, but then we can label exactly. Since it's not right on a grid line, I'm going to go ahead and label that one. I think I'm actually not quite steep enough. If this is around, that's okay though. So this is actually slightly steeper, but it's a good approximate shape. All right, thank you for watching.